Okay, so let us continue with what we were discussing yesterday regarding the estimation of wave load on a single member. That means one single structure element is subjected to wave loads. It is quite easy, but when you have multiple elements, we will look at a procedure which we can find out. So, in this I think various steps we were trying to understand. The first one is to collect data on the wave height, wave period and the direction, and the associated wave theory for a given situation. Basically, we learned about little bit about the linear wave theory and the nonlinear wave theory, and where it is applicable, what are the assumptions are violated in case if you select a wrong wave theory. So, basically we want to see that how do we select a wave theory, and then the using a particular wave theory that you have selected, estimation of, note the word I am using, estimation is always is not 100% correct. All these wave theories are just near approximation of what is the natural phenomena happening in the open sea conditions. So, always we try to estimate, correct it, adjust it according to what we think it is right. So, basically most of the wave loads are not calculated, is actually estimated based on certain ideas devised by past people like researchers over a long period, and we keep updating this information and as we learn more and more. So, there is absolutely no question like this is right and this is not right, still we keep updating because most of them are semi empirical. So, in doing so we also need to select a suitable CDCM which is highly subjective to experimental evidence, and then the other 3 or 4 parameters we are just going to look at what are these correction factors. So, you evaluate the wave force and do a correction to adjust to reality. So, some of these correction factors like wave kinematics factor, conductor shielding, and then the blockage factor will tell you the story that the reality versus the theoretical calculations, there is an adjustment to be made. And the one more extra parameter is the marine growth. You might have seen, if you have traveled to coastal areas, you will see that the algae grow on top of the structure wherever you have coastal structures or even offshore structures. These algae grow on top of the structure, making the structure slightly the dimensions bigger, but of course, it is not a structural element, it is basically a attachment that makes the dimension bigger. Once the dimension becomes bigger, what will happen? Your wave loads will be larger, that means the attractive more forces. So, you could see here that picture I will show you something like this. You see this picture on the left side is about a meter diameter structural element, which is a column of a jacket structure. You could see that how much algae grow on top of this, could be 30 to 40% diameter increase. You could see that potentially the wave loads on this and this is definitely going to be higher because of the presence of such a additional dimension. So, sometimes we do use basically a idea using the natural wave energy to remove this. So, you see on the right hand side we call it marine growth preventer. The idea behind is a sliding system by natural water oscillation, just because wave is moving up and down. So, this will scrub on top of this member, making sure that there is no algae continuously growing on top. So, if there is a little bit growing there, it will keep moving up and down because we are not using external power. So, this is one good idea that we could come up, but then the reliability of this is little subjective. Sometimes it may get entangled and then become very good place for growing further algae, So, basically sometimes we do use this, but not 100% going to help us. So, basically if you look at this marine growth is a phenomena which cannot be prevented. Number 1, for sure you can't prevent, it is going to grow, and then how we take into account is something that we need to think about it, because the diameter increases, but it is not going to offer structural strength, it is only a burden for us. It increases the weight, it also increases the dimension which will capture the more wave and current loads. So, that means we need to consider this as a separate analysis in the hydrodynamic load calculations. Typical dimension or the thickness of this is about 5 centimeters to 20 centimeters. Sometimes I have seen in some of the locations 20 centimeter is the kind of thickness. So, if you have 1 meter, it becomes 1.4 meters, 20 centimeter this side, 20 centimeter the other side. So, but this one varies most of the time along the depth. You know, algae is a living organism, so you need definitely oxygen. So, as you go down, what will happen? The oxygen content is lower and lower, and that means the thickness or the amount that it can grow at bottom sea near the seabed will be very minimum. So, you can see that the near the surface it will be larger and slowly reducing down. So, this effect is actually not very good for us, because the wave load is also maximum at the top only, because of the water particle kinematics is higher, velocity is higher, acceleration is going to be higher. So, you could see that this is an added effect which will produce more loads. So, this needs to be definitely taken into account, and also adds weight. You see here the member becomes so large, even if it is light density, it is not very heavy like steel, but still it adds weight. So, we will see that so much of members you have in the jacket structure, every one of them added with so much weight, you will see that the total foundation design load will be higher. So, that is one effect which we need to definitely address in a proper way, and so that you know, the loads are captured correctly. The other three parameters are generally a reduction factor, wave kinematics factor, and conductor shielding and current blockage. The same steps what you have just now seen is given in a chart form, which is given by API. In fact, if you see that the whole chart is developed by API, just to make sure that you do not forget, it is not a technical flow chart, it is basically an idea that you should keep everything in mind while doing evaluation of wave load on a structure. Basically, the collection of wave data 100 year, 1 year, associated current, and then combine them, and then the wave theory selection depending on water depth, wave height, and the location, including Doppler effect. We are going to just see what is the Doppler effect, we will just see in the next few slides, and then calculate the water particle kinematics, and then use the reduction factor like wave kinematics factor or current blockage factor, and then come up with the combined wave and current effect. You know, we will see the nonlinear interaction as well as the Doppler shift, and then basically apply corresponding CDCM for a particular member, whether it is circular sections or rectangular sections or other shapes, you will have the CDCMs different, and then apply the marine growth on top of them, and then if you have any secondary structures, non-structural elements, apply there, and then the conductor shielding, and finally you come up with the distributed forces, and then vector sum means you distribute into x, y, z directions for a 3-dimensional structure. If it is just a vertical structure, it is very simple, but if you have a 3-dimensional brace or column, you can see that then global forces can be computed. So, you see this, the reason why this flow chart is given is to make sure that you do not miss any one of them, because it involves several sub activities. Selection of wave theory, you see on this right side you have a chart made by a task force set up by API quite some time back, and basically came from Atkins report. Is actually a laboratory in US, they have got a very good setup, they have been doing hydrodynamic research for several decades. So, they came up with this, in fact this chart originally, and then the API task committee trying to identify what could be the best way of classifying wave theories for the purpose of computation of wave forces. So, this chart is adapted, but modified, the API task group slightly modified the Atkins original chart. So, you can see here in the horizontal axis you have a d by gt square is a representation of the depth of the water depth at the location with respect to gt square is proportional to the wavelength. You know, the longer the wave period, longer the wavelength. I think you can see very easily 2 second means is, once you go into wave theory calculation you will see basically the length is proportional to the period, for sure you can easily understand. So, the gt square is a representation of the length of the wave, and on the vertical axis you have h by gt square, basically the wave height versus gt square, that means also with respect to. So, you could actually indirectly write this one, the vertical axis is h by L, whereas the horizontal axis is d by L. So, water depth in relation to the wavelength and wave height in relation to the wavelength. So, one is the wave steepness, the other one is the relative water depth, how much is the water depth with respect to the length of the wave. So, you could see here these two parameters are playing major role. One is the vertical one is very easy to understand, the wave steepness, how big is the wave when compared to the length of the wave. The longer the wavelength, smaller the wave height, the assumption made by Airy could potentially be acceptable, whereas the wavelength is smaller, wave height is too big, probably the assumption is going to be violated. So, very simple idea that vertical axis is trying to figure out how relative wave height to the wavelength, that is what the idea behind. The horizontal axis is also very easy to understand, water depth versus wavelength. If you look at the wave decay function which we discussed about the sine and cosine hyperbolic functions, the wave effect is going to be diminishing as you go down. So, if you look at that, you will be able to understand the deeper the water depth, for example 1000 meter versus 100 meters, just take an example, 100 meters 100 meter wavelength, the effect will be almost to the full depth, whereas 1000 meter water depth, same 100 meter wave, you will see that the top portion will be having water disturbance more than when you keep going down. So, that you can see that the D and the length effect you could potentially identify, probably you will learn more in the hydrodynamics course, that the water depth in relation to the wavelength also play a major role, how much is the distribution of the wave load from surface to seabed. So, the D by L is larger, means the depth is more in comparison to the wavelength. You will see that it is more like a deep water effect, means the wave forces is concentrated on the top 1/3 or 1/4 of the total depth, and that is the representation given by the horizontal axis. So, based on these two parameters, you could see here the theories have been classified and selection is made easy. If you see on the on this side, linear or stream function wave theory, just you can see on this blue line from here all the way. So, any of the points lying here, you can simply select linear wave theory. That means, you could see that it is a lower h by L, number one, basically the wave height is smaller in comparison to wavelength, and also the water depth is deeper, because as we go on the horizontal axis on the right hand side, is water depth is deeper in relation to wavelength. So, that means is deep water, no breaking, no build up. So, basically that is the idea behind that you will select linear wave theory on when the d by gt square is larger number. As you come smaller and smaller, you will see that the shallow water effect, that means the wave will be effective throughout the full depth or as much as distributed to a full depth. So, that is why you will see a shallow water waves, or you can even see stream function wave theories. So, in here there is nothing wrong even if you use stream function wave theory, but also can select. So, you could see that this demarcation, this line beyond which you can't use the Airy's wave theory. So, the linear wave theory cannot be used all the time unless these parameters are such that they are below the first blue line. I think that you could easily understand. Then when you exceed beyond that line, then you have several choices. You can use Stokes wave theory, you can use stream function wave theory, and then you have the last upper line beyond which the wave does not exist because of wave breaking. So, you can easily see that as the height increases without changing the wavelength, what will happen? The height of the wave is higher and higher, is unable to sustain, it is going to break. So, that we call it deep water breaking, and basically the waves cannot sustain because of the water particle kinematics is so large compared to the speed of the wave. You will see that the water particles jump in ahead of the wave propagation. I think that you will learn in hydrodynamics course more. So, basically that gives you an idea about the demarcation of shallow water, deep water, and breaking and non breaking waves. So, the upper line, the upper limit, what you see here, as long as h by gt square is higher, the waves will break. So, you may not be able to apply any of these wave theories, because you can see there when we derived, or in fact the boundary conditions and the domain equations is for continuous or flow within a domain. If you have a breaking wave, the water particles get separated, none of these theories will be able to apply. That is why you cannot calculate a wave force for a structure when the wave is just breaking or just broken. So, what we need is another idea. When the wave is breaking on a structure, you will see when you go to many of the port and harbor structures or coastal structures, many times waves come and break on the structure. So, how do we estimate? So, we need to just see some alternative methods, because on none of these methods will work, because they get separated during wave breaking. So, this is a very good guidance for us to select a theory, because it gives a little bit of sense, wave height effect, water depth and relative wavelength effect. So, typical example for a location, what you see here in this chart is the water depth is 60 meter, wave height is 12 meters, and then associated period is 10 second. Calculate this both the parameters, and then you could see that straight away Stokes wave theory is applicable. So, for a typical jacket location of 60 meter water depth, you could see that the wave height is potentially 12 meters, Stokes wave theory. So, you can't use Airy's wave theory, because the wave height is at the same location. If you select 2 meter wave height, you will see that probably it will come down straight away here, is not it? Automatically you will be able to select Airy's wave theory. So, that is similarly when the water depth become 10 meter, for example, can we have a 12 meter wave height? Not at all feasible. It will not be possible to propagate, because by the time it reaches 15 meter itself, it would have already broken, because enough water depth is not available. But at that location 10 meter, you may be able to get 2 meter wave height. So, 10 meter versus 2 meter, you may still fall in either Stokes or Airy's wave theory, we do not know. So, it is all relative, rather than 60 meter is called a deep water and 10 meter is called a shallow water. There is no such thing. Every time you have to see the relative effect of water depth, wave height and the wavelength or wave period. And the next one is the selection of direction of wave, which I think is as important as what we are trying to do using estimation. Basically maximizing the loads on the structures. The other day we were discussing about the diagonal direction could potentially be proven to be the most effective and higher forces could produce because of the decoupling effect. So, basically in here you can see several times we do also ask for a variation, instead of only directly doing diagonal, you could do plus minus 5 degrees, plus minus 10 degrees, depending upon uncertainty at the site. Not necessary that only 8 cases, you can even do 16 directions, because it could be possible at the site. But as a thumb rule, minimum 8 directions for a rectangular structure, for a triangular structure minimum 12 directions, which is mandatory, without which you will not be able to get the design approved. The next one is the Doppler effect, which we need to just spend little time. Basically now you have seen the Morrison equation, which I think drag component, and you have the inertia component, and in that the velocity is a combined velocity from the wave and the current. We need to add the current, because every location, every offshore field, you may have sea waves, you may also have the sea current, and potentially the API or any other code is asking you to actually apply in the same direction, though sometimes you may have different directions. So, in order to maximize or take into account the worst possible scenario, we need to assume that the wave is propagating exactly in the same direction of the current. So, imagine the wave is propagating in the forward direction and the current is also flowing in the same direction. What will happen? The wavelength will get stretched away, it will increase in length because of the Doppler shift effect. If the current is coming exactly opposite, the wavelength will get reduced. So, this phenomena is supposed to be taken into account. As soon as you change the wavelength or wave period, you could see here in this chart that wave theory will get modified. That is why you see here I have put T apparent, nothing but the modified wave period. The original wave period is say T, and because of the presence of current in the forward or backward direction, you may see that the wave period may increase or decrease accordingly. API has come up with a chart something like this. So, you can see here, if it is a 0 current, is a current ratio, the VW is the current speed divided by GT. If it is 0, the ratio is 1, is not it? Basically you just go up here and then just come here. Several experiments have been done, and basically based on this, that red line is something that we normally use. So, you could see here forward current, the ratio is always higher, and backward current or reverse current, in order it will always be smaller than 1. So, that means the wave period is 10 second. If the current is flowing in that forward direction, depending on the speed, the larger the speed, that means the number could go up to 20% larger or even 25% larger. So, 10 second will become 12.5. So, basically 25% larger. So, the wave period becomes longer, or if it is opposing current, then you will have the. So, the same thing is calculated by a simple relationship called a dispersion relationship. You will derive this one when you go into your hydrodynamics course next few days, the relationship between wavelength and the wave period, which I purposely did not derive because it is again a waste of time, because you will be deriving in your course. So, basically that is the relationship that you can see, relation between the wavelength and the, as long as you are given a wave period, you could find out what is the wavelength using this, but unfortunately you see here this equation is a iterative equation, because the wavelength appears on both sides. So, you have to assume certain wavelength and then start iterating until both side becomes equal. So, basically, or you may be given a table, wave table will be given to you in your classroom exercises. Probably once they give you that, then we can do a example problem in our class. I think you will be given definitely. So, that you can, if you are given a wave period, and typically you can use the table to find out wavelength. Once you find the wavelength, you can find out all the parameters like velocity, acceleration, because if you go back there, you need wavelength to start the computation, and then once you have the wavelength, calculate the velocity, acceleration, substitute into Morrison equation, find out the wave force, and then do further steps. Okay. So, basically how it is calculated, basically the L by T is the wave speed, length travelled by one wave cycle, and that original is this and the modified is this. The effect of current is added, again the current speed is going forward. So, if it is negative, you will just detect it. So, it's a simple Doppler effect. Now comes the important, so all of you understand the idea behind the reduction or increase in the wave period or wavelength, just because the current is flowing in the forward or reverse direction with respect to the direction of wave propagation. Now, the second thing is whether we should do wave force separately or current force separately or combined together. So, you see this equation, the drag force is non-linearly proportional to the velocity. Now, if you imagine we have wave is going in the same direction of the current, you could also think about, okay, I will do the calculation of wave force separately plus add the wave force with the current force calculated separately. So, typical example you see here, the all other terms are constant, like diameter, density, everything is kept constant. So, the only changing is the velocity down here. So, now if you take the velocity component, split into two components, one from wave and the other one is from current. So, you could see here, if you calculate the forces separately, what will happen? If current velocity is 2 meter per second and the wave velocity is 3 meter per second. So, if you do this computation, 2 square plus 3 square will become how much? Basically 13, because computation was done separately for current and wave. Now, if you just add vectorially the wave velocity plus the current velocity together and then do the computation of the force, you will get 25. That is exactly the idea behind the nonlinear drag term cannot be treated individually for wave and current separately, because since the wave and current is acting in the same direction, you should add the velocities before computation of the forces. So, you must remember, whenever you are trying to do, you can't do separate calculation for wave forces and the current forces. You should add them together before you substitute them into the Morrison equation. Whereas, you see here the inertia term is anyway linearly proportional. So, not a big deal, but however, current will not produce any acceleration. So, you do not have a problem down there. I think we have seen this Marian growth. Again, we should take into account this effect. So, these other three reduction factors which I think I mentioned about it, we should consider. The first one is the wave kinematics factor, very important. You know what we have seen is a two dimensional wave theory, which we have seen the equations, and if you compare with the reality, you could see that the water particles are not going to flow in such a nice manner because of the three dimensional effect of the wave. You will not see a wave nicely, like if you go to our wave flume, you will see that the waves are produced almost close to the theoretical wave, like what you see in the textbooks, but still there exists a distortion, side wall effects, and probably slightly different from, even if you do comparison with your theory and the laboratory simulated waves, you will find some difference. But if you compare it with the actual open sea condition, you will see always open sea condition is lower than the theoretically calculated velocities and acceleration. It was proved by in fact Morrison time itself, they have done prototype testing by doing measurements offshore and measurement laboratory and then do the computation. They found that always the theory is giving you the larger value than the measured values. So, what they were coming up is a reduction factor. If I have a 12 meter wave height or 10 meter wave height, I do computation, I simply reduce by 8 to 10% irrespective of geometry. Remember, the CD and CM was taken into account to modify, because the CD CMs are only a correction factor again, basically that is for particular geometry. In addition, for overall any type of geometry, you simply can reduce 80% or 90%. So, this is recommended by the API task committee, which was giving you recommendation, because 10% of wave load could substantially reduce your design reasonably. So, that is why this reduction factor, the wave kinematics factor, is basically to account for the difference between the two dimensional wave theory versus three dimensional wave effects in the real ocean. The last two is basically the current blockage factor and the conductor shielding factor, is again also to account for kind of reduction only. So, always all these three factors will be less than 1, cannot be greater than 1. So, you will see this current blockage factor, when you put a big structure in middle of the ocean, you could see that free stream current is unable to flow across the structure, gets diverted, probably slow down and then go around. So, because of that effect, possibly the loads on the individual elements could be lesser than what it is supposed to be if you have only one single element, because it is a assembly of structure is placed in the middle of ocean. So, you will see that the reduction could possibly happen. API has done a lot of studies on this respect, and they have recommended for each type of jacket structure, 3 leg, 4 leg, 6 leg, 8 leg, they got a reduction factor in the order of 15% to 10%, like the maximum that you can go here is 0.9 and the minimum is 0.85. So, you could see that for broadside is given as 20% reduction, whereas the end on direction, the smaller dimension, is given as also similar, only diagonal direction has given just a 15% reduction. So, once you calculate the wave force, you reduce by, you multiply this number, basically you just multiply by 0.8 or 0.85 depending on. The last one is very interesting, basically the shielding factor. When you have one structure in front of another structure, basically the water flow, the water particle velocities and acceleration is going to be obstructed by the front one. So, you could see that if you keep them together just like side by side, only the one of them will be receiving load, but if you keep them few meters away, you could see that both of them will get, because the water particles will come back to the original position after diversion and then come back. So, basically that is why we have this effect called the conductor shielding factor. API does not recommend the shielding effect to be considered for all the members, except when you have vertical members arranged in sequence like conductors. I think I have shown you some pictures. What is conductor? Is a well protection casing. So, basically if the spacing is so small, this spacing between the front one and the back one. You could see a chart developed here. As long as the spacing is about 4, the shielding factor becomes 1. So, 1 meter diameter, if you keep them 4 meter away, then there is no shielding effect, but if you bring them closer and closer, you could see that potentially reduction in the loads, because the second one does not get full effect. So, if you see here, if you keep it at 2 diameter, it becomes almost half load only. So, you take 2 cylinders, one cylinder calculate the force and the second cylinder receive only 50% of the load. It is the same diameter cylinder. So, but the second one only receives 50% because its close vicinity allow the water particles to move away from the second cylinder. So, that is the idea behind. So, if you have series of cylinders, the last one may get nothing because its free stream is not going across the section. So, this effect will also be taken because sometimes each of the platform will have a many conductors. So, you do not have to really take every one of them individually. Selection of CDCM again basically is a empirical coefficient, very similar to you might have studied a selection of wind drag coefficients for calculation of wind force on structural elements, basically for rectangular projected surface, tubular surface, streamlined body, each one has got a different drag coefficient. So, similarly here we have the drag and the inertia coefficients, which are correction factors to Morrison equation. Remember, these are the numbers you have to select according to the size, shape and the type of flow. That means, whether the wave is 10 meter wave or 1 meter wave also will get changed. So, that is why lots and lots of research has happened over the last 50 years. If you see this chart before we go anywhere else, many people have done research. You see here at the bottom, starting with you know, where is this Morrison, Sarpakaya, he has done so much of work as early as 1970s and 80s, and he has, if you look at his book, he got a lot of collection of more data. But of course, the API task committee has taken only the good work and collected and presented here. You could see the variation is very large, sometimes it is so low, sometimes it is so high. So, what they have come up is, they have come up with this red line, which is drawn something like this and presented with respect to a number called non-dimensional number called Coulligan-Carpenter number in the horizontal axis, and the vertical axis is Cm. So, what is Coulligan-Carpenter number? Is a representation of the wave period with the diameter of the member. So, u is the velocity at the crest or the maximum velocity including current, t is the half or T2 is the half wave cycle or period, d is the diameter and k is the Kc number, which is to represent the type of flow in relation to the size of the structure. So, most of the literature you will see that the presentation of empirical coefficients for wave load calculation is given in terms of k, but in the recent times some of them have been modified to Reynolds number. I think you might have studied Reynolds number, again indicate the type of flow, whether it is slow or fast or super fast, the velocity times the diameter divided by your kinematic viscosity. So, this is also a representation of how relative to the structure the flow conditions, which will give you an understanding. The larger the speed, what will happen? The negative pressure will happen at the tail end of the structure, which means the contact between the fluid and the structure is very less. So, basically boundary layer effect will come into picture. So, Reynolds number, usage of Reynolds number or Coulligan-Carpenter number depends on type of presentation. Some textbooks will use Coulligan-Carpenter number, some may use Reynolds number, but API have choose to use the K number as the representative to identify the flow conditions. In fact, most of the presentation in offshore we use K number, and basically you see here starting with 2 and reduce to 1.6. So, that is the range of values of Cm. So, if you are asked to come up with Cm values, do not go and put some big numbers or small numbers, it will be in very small range 1.6 to about 2.2. So, it should be between, and this is for tubular members. Remember, this is for circular sections either placed vertically or horizontally or in any 3-dimensional fashion, but for non-tubular sections this could be substantially different, it could be higher or more. Similarly, you see here another chart for drag coefficient, again presented with respect to k number, but instead of directly presenting, they have given a ratio of drag coefficient with the CDS. CDS is the surface roughness coefficient. Surface roughness is to be taken as 1 for smooth cylinder like structural steel pipe. If you have marine growth, then there could be potentially increased roughness, because you saw that picture, no, the marine growth is so rough. So, you have a increased coefficient, maybe 1.1, 1.2, so CD will be slightly increasing. So, in here what we are trying to say is, you have to select CD and CM suitably according to the type of structure, type of roughness of the surface, and use it with the Morrison equation. And you can also use DNV codes, because API does not give you or talk about non-circular sections, they always focus on tubular sections. So, I have just summarized in the next few slides recommendations given by DNV for various non-circular shapes, which could be potentially useful. Typically, the CDCM for tubular sections I have just taken from API 0.65, 1.6, 1.05 and 1.2. This is for smooth cylinders, this is for rough cylinders, like what you have seen with marine growth. You could see that the drag is increasing and the inertia is reducing, and this is true only when you have this UT by D is greater than 30. This is a condition given by API, these numbers are valid. If it is not valid, then you have to use the charts to select your own coefficients and then apply. So, I have just summarized from DNV code that you have large number of, you can just go through, you can see from there, you see here the added mass coefficient basically is 1. That means, if you have one cylinder, the structure is moving in water, the additional mass moving with water is basically the same as the displaced volume of the cylinder itself. So, that is why you will see 1 plus 1, you understand the idea now. Cm is equal to 1 plus Ca, Ca is added mass coefficient, which is this. So, this Cm, whatever you have obtained from experiments, could also be theoretically estimated by simple means. If you put a circular cylinder in water and when it is moving horizontally, the amount of water moves together is almost equal to the displaced volume of the cylinder itself. So, the cylinder volume plus additional volume surrounding the cylinder. So, almost 2, that is why you see here starting with almost equal to 2 or 2.1, 2.2 and then gradually reducing as the flow speed increases. So, basically you see here circular cylinders to flat plate, all geometrically derivable dimensions given are recommended by DNV, but this needs to be verified by experimental conditions. Most of the time we take this as a basis and then do the experiments to verify. Similarly, I have given you the drag coefficient also recommended by DNV for non-circular shapes, like for example, wires and chains with rough surfaces. Most of the values are around 1.5 to 2.4. Flat plate is something that we are very much interested. If you see there, this kind of flat plates, CD is almost 1.9. So, comparison to what we had was 0.6 and 1.2 for a flat plate, so much of drag force is attractive, and other shapes you could use it for your reference if you encounter in your design problems. Now comes the most important. So, we have learned the summary of the whole thing is, we know how to select wave theory, right, calculation of water particle velocity, acceleration. The components in the Morrison equation is drag and inertia, and in the drag we have to combine the wave velocity and current velocity together. Before we do that, selection of CDCMs, application of reduction factors, increase of diameter by marine growth. So, all these ideas have been understood. Now, we need to see how we can calculate the maximum force on a vertical cylinder. Just you see from this picture, we have a vertical cylinder and the wave is progressing in a direction perpendicular to the cylinder axis and just moving continuously. So, at what instant of time maximum force will come, which needs to be evaluated. So, what we can simply do is we can just take this Morrison equation, you can take this equation, C d is a constant, rho w is a constant, d is a constant, v is a variable depending on the location, is not it? Location means it could be horizontally or it could be vertically, but right now we have fortunately have only one cylinder, vertical cylinder sitting on seabed. So, we have got various points along the cylinder, x is equal to 0, we can set the coordinate system in such a way that the axis, vertical axis becomes x is equal to 0, only z will be varying. So, you substitute that equation in this, because you already have the potential function, you already have selected the del phi by del x, substitute in this equation. Similarly, you can substitute the equation for the acceleration, because everything else is a constant, for example, pi d square by 4 cm rho w, and you substitute and you derive a equation for f t. The only variable will be the time and the depth, because it is going to vary along the depth, it is going to vary with respect to time, because if you go back and see the equations which I derived, if you see this equation, you are going to substitute the equation for velocity, you are going to substitute acceleration. So, if you look at this, z is the variation with respect to depth and t is the variation with respect to time, because x has become 0, because we have set the coordinate along the vertical axis, your horizontal axis starts. So, if you substitute, only two variables are there. So, along the depth you can see velocity is going to come down, for sure you can substitute and check. With respect to time only, we do not know what could be the, but since it is a cosine or sine function, it is going to vary something like this, either a sine function or a cosine function. Now, what we are looking at, not that information, because we want only the maximum value of the force at any one time during one wave cycle, because it is going to be repetitive. The assumption that we made is a complex waveform is decomposed into simplified waveform like sine or cosine wave, so that only one waveform you look at it, the remainder is repetitive. So, that in that one wave cycle, where is the maximum force is our interest. So, we go back here, there are several methods of doing it. The easiest method is divide the whole cylinder into several pieces, like you see here, something like this. So, if it is 10 meter, divide the cylinder into 10 1 meter pieces, is not it, and each piece you take it, you have a coordinate, x is always going to be 0 because it is a vertical cylinder, and z is going to be 0, minus 1, minus 2, minus 3, minus 4 up to minus 10. So, each of these location you can calculate the velocity and acceleration, because you know x coordinate, you know z coordinate, use the formulas given there, calculate this and then substitute into Morrison equation, is not it, each of the location. So, for time t is equal to 0, you take the equation, find out the acceleration velocity, find out the forces. So, you plot that and you will see that something like this, because near the surface velocity is going to be higher, because the exponential decay function, because if you see the velocity at the bottom you have sine hyperbolic kh and at the top you have cosine hyperbolic y plus or z plus h. As the z goes down, you will see that the function will be reducing. So, you could see that the velocity and acceleration is definitely going to reduce as you move downwards. So, this kind of function you will see. So, when you calculate the force also, you will see something like this. So, t equal to 0, you calculate 1 like this. All of you understand this idea, no? So, x is 0, z is varying, and we divided the whole section, whole member into several subsections, and each of the subsection take the center coordinate z equal to whatever number comes, calculate the velocity, acceleration, all other terms are constant, substitute, you find out the force on each element multiplied by that 1 meter. If you decided to divide by 2 meter, then you have to multiply by 2 meter. In this case, we have divided by 1 meter, which is very convenient. So, each of the segment receives one force proportional to the diameter and the segment length, because you have taken the central coordinate x and z and you calculate the force for all elements, you plot them this way. Now you see some pattern. Now you can do a numerical integration. You might have studied several numerical integration procedure, or you can do a simple weighted average. I think most of you will know in numerical methods. So what is weighted average? Just add the each coordinate and divide by 2 for each of the blocks, and then total summation, you will be able to get the total force. So you understand the idea behind how we do divide into several sub segments. Each segment you calculate the force, each segment use the coordinate to calculate the velocity acceleration, substitute into Morrison formula, and so this force corresponds to only one time instant, because the wave period is 10 seconds. So t equal to 0 you have calculated. Now we have to repeat this for several time steps from 0 to 10 second. You divide every 1 second, you divide every half a second, it is up to you, isn't it? We will continue tomorrow.